Search that understands what you mean. Recommendations that just work. The memory behind every AI assistant. They all rely on one thing underneath: a vector database. This is Qdrant. First, the core concepts. What a vector database actually stores, and how it finds similar items so quickly. A vector database stores high-dimensional vectors instead of plain rows. Each vector is a numerical fingerprint that captures the meaning of a piece of text, an image, or audio. Instead of matching exact keywords, Qdrant finds the nearest neighbors in this vector space, the items whose meaning is closest to your query. That makes it the backbone of modern AI search and retrieval. An embedding model turns raw text into a list of numbers, a vector. Similar sentences map to nearby points, while unrelated ones land far apart. In this training, we use the all-mini-LM model, which produces 384 dimensions for every piece of text. Those vectors are exactly what Qdrant stores and searches. To compare two vectors, Qdrant measures the distance between them. Cosine similarity looks at the angle between vectors and is the most common choice for text embeddings. Dot product and Euclidean distance are also supported. Whatever the metric, the idea is the same. A higher similarity score means the two items are closer in meaning. Comparing a query against every vector is accurate, but slow. Instead, Qdrant builds a navigable graph called HNSW, where each point links to its nearest neighbors. A search walks this graph, hopping closer and closer to the best matches in just a few steps. This is Approximate nearest neighbor search, and it scales to millions of vectors. The unit of storage in Qdrant is a point. Every point has an identifier, one or more vectors, and a payload, arbitrary JSON metadata, such as a title, category, price, or timestamp. That payload is not just along for the ride. Qdrant can index it and filter on it during search, so you combine semantic similarity with exact conditions in a single query. Points live inside a collection, which is the equivalent of a table. Under the hood, a collection is split into segments that can be optimized and indexed independently. For scale, a collection is divided into shards spread across nodes, and each shard can be replicated for high availability. You get all of this without managing it by hand. Qdrant chooses how to search for you. When a segment is small, below the indexing threshold of 10,000 vectors, it simply scans everything with exact search, which is fast and perfectly accurate at that size. Once a segment grows past the threshold, Qdrant builds the HNSW index and switches to approximate search automatically. You never flip that switch yourself. Qdrant supports two kinds of vectors. Dense vectors come from neural models and capture meaning, so they shine at paraphrase and synonyms. Sparse vectors, like BM25, capture exact keyword matches and excel at rare or specific terms. Dense vectors are short and packed. Sparse vectors are mostly zeros with a few strong weights. The best systems combine both. Qdrant ships as a single Rust binary. It exposes both a REST and a gRPC API on ports 6333 and 6334, and it bundles a web dashboard so you can explore data with no extra tools. The performance-critical core, the index, storage, and filtering, is written in Rust. You can run it in Docker, in the cloud, or embedded on the edge. Now the fun part, the capabilities. Everything here was tested live against a Qdrant server loaded with 4,000 news articles and 600 products. Semantic search is the headline feature. We embedded the query, "A sports team wins the championship game," and Qdrant returned articles about basketball, baseball, and the Olympics, even though none of them contain those exact words. Results come back ranked by similarity. This is the retrieval step behind retrieval augmented generation. In code, it is just a few lines. You embed the query text, Then call query points on your collection with the resulting vector and a limit. Qdrant returns the closest points with their scores and payloads. Notice there is no SQL and no keyword logic. Similarity does all the work. Dense search understands meaning, but can miss exact keywords. Sparse BM25 nails keywords, but ignores synonyms. Hybrid search runs both at once, then merges the two ranked lists with Reciprocal Rank Fusion, so the result combines the strengths of each. Qdrant does this fusion server-side in a single request. Here, hybrid search runs on the query Google Stock Market IPO. Dense retrieval surfaces semantically related business stories. BM25 locks onto the exact phrase, and Reciprocal Rank Fusion blends them. The fused list promotes the document that exact matches the keywords, while keeping the strong semantic hits right behind it, all from a single request. The code adds a prefetch for each retriever, one dense, one sparse, and then a fusion query using RRF. Qdrant fetches candidates from both, fuses the rankings, and returns the final top results. You never have to merge lists in your application code. Filtered search combines vector similarity with hard constraints on the payload. We asked for comfortable shoes for marathon running and limited results to the running shoes category in stock, rated 4 stars or higher under a price cap. Qdrant applies these filters inside the index traversal, so every result is both relevant and valid. You build a filter with must conditions, a keyword match on category, a range on price and rating, a Boolean on stock, and pass it alongside the query vector. Because those payload fields are indexed, filtering stays fast, even when the conditions are very selective. The recommendation API needs no query text at all. You give Qdrant the IDs of items a user liked, and optionally, some they disliked, and it searches the vector neighborhood around the positive examples, while steering away from the negative ones. From a single liked laptop, every recommendation came back as another laptop. It is more like this built in. In code, you call query points with a recommend query, passing positive and negative point IDs. Qdrant pulls the stored vectors for those points, combines them, and returns the nearest neighbors. This powers product recommendations and content discovery without a separate model. Because everything is vectors, we can project them down to 2 dimensions and look at them. Plotting 1,000 news vectors, the 4 categories form clearly separated clusters. That geometric structure, similar items grouped together, is exactly what nearest neighbor search exploits, and it is a great way to sanity check an embedding model. Qdrant exposes its own configuration and statistics. One detail worth knowing: our news collection reports 4,000 indexed vectors because it carries a sparse vector, and sparse vectors are indexed immediately. The products collection shows 0 because its dense vectors are still below the indexing threshold and are served by exact search. Qdrant manages that transition for you. Finally, let's tour the built-in dashboard, a full web interface served by the same Qdrant binary with no extra deployment. Open the dashboard at port 6333/dashboard and you land on the Collections view. Each collection shows its status, point count, segments, and shards, plus chips describing its vector configuration. At a glance, you can tell that our news collection carries both a dense and a sparse vector, ready for hybrid search. Inside a collection, the Points tab is a visual browser. Each card shows the stored payload and the vectors with their lengths. You can filter by a payload key and value, paste a point ID to find similar items, or jump straight into the similarity graph, all without writing a line of code. The console is a built-in REST client. Type any API request. Here, a scroll that filters the news collection to the business category. Hit run, and the JSON response appears beside it in milliseconds. It is the fastest way to prototype a query before moving it into your application code. The Visualize tab projects your vectors into 2 dimensions right in the browser, coloring each point by a payload field so the clusters jump out. The Graph tab turns the data into an interactive network where each node links to its nearest neighbors, perfect for explaining and debugging similarity. The dashboard rounds things out with extras. Datasets let you import ready-made collections with one click. Interactive tutorials walk through filtering, hybrid, and sparse search. And the Access Tokens page generates scoped, expiring JWT keys with per-collection read and write permissions. Everything you need for secure, multi-tenant access.
If you like this video, please subscribe and share. Thank you.